In this video, we will answer one question. What is the frequency response function? Why is it useful? We begin with simple example. We have the black box, which has one input and one output connector. We don't know what electronic is inside. We can just send the input signal in and we can measure what happens on the output. For simplicity, we will use just DC voltage as input signal. For example, 1 volt. We send it to the input, and from the output returns 2 volts. It means that the box gains 2 times. Now we send 10 volts to input. From output returns 20 volts. The gain is again 2. The value of gain is the response function of the box. We suppose that black box has the constant response gain. It means that the gain is the same for all values of input voltage. If it wouldn't be true, then we get different response value for different input voltage. We will not analyze such boxes in this video. We suppose the constant response value. Now we add the AC voltage to the input signal. For example, 1 Hz frequency. And again, we can read the response on the output. For example, we send in the 1 volt RMS and box returns 5 volt RMS. The response gain is 5. Now we have the gain of DC, it is 2, and the gain of 1 Hz, it is 5. Now we can add next frequencies, 2 Hz, 3 Hz, and next. For example, the last frequency will be 400 Hz. We measured all response gains, so we get 1 DC gain and 400 lines of AC gains from 1 to 400 Hz. It looks like spectrum with 401 lines. That is true. It is very similar, and actually that is the frequency response function. In next example, we use the noise as input signal. The noise has flat spectrum. It means the amplitudes are almost the same for all frequencies. The equalizer is used as black box. We set one gain on 400 Hz and second gain on 4000 Hz. If we would have the mechanical structure, then it would represent 2 resonant frequencies. Now we can send the noise to equalizer and to the channel 1 of VA5. The signal which returns from equalizer output we connect to channel 2 of VA5. Now we set the frequency response measurement FRF. For this example with noise, we can use standard Henning windows for both channels. We use also averaging. Now you can see the result. The response graph has the same shape as we made on equalizer. On y-axis we can see the gain levels for every frequency. Now please note this line. It is the coherence function. You can see that it is constant for all lines, it means all frequencies. The value is equal 1, but don't be confused that on y-axis is different value. The y-axis is used for response values. We would have to draw the second y-axis for coherence. The coherence is constant and equal 1 because the response of the equalizer box was the same for all measurements in averaging. It means the response was stable. If the response of black box is not stable, then coherence decreases to lower values. If the response is random, then coherence is 0. It means there is no relation between input and output. One simple example. I change the gain of 400 Hz for every measurement in averaging. We can see the result. The coherence drops down. The response was not stable. In next example, we disconnect the equalizer output. It means the noise from generator is in VA5 channel 1 and random noise is in VA5 channel 2. There is no relation between them. You can see that coherence drops to 0 on all lines. When we look at coherence only, we can see the amplitudes around 0. If we look at response function again, we can see several resonances, but the coherence is almost 0. It means these resonances are just coincidence. If we will repeat measurement again and again, we will get always the different result. What does it mean for practical measurement? We can use only lines with high coherence. We can predict the response reliably only on these frequencies. The response on frequencies with low coherence is unpredictable and random, and we cannot use it in practice. Thanks for watching.